but let's get started. Good afternoon, everyone, and welcome to another session in the Food Collective webinar series with Anton Paar. Our aim with this series is to learn from experts across the food industry. And then today's webinar is presented in collaboration with Anton Paar, one of our valued premium members on the Food Collective. Anton Paar is internationally recognized for developing high-precision laboratory and process instrumentations used throughout the food and beverage industry. Their technologies support manufacturers in measuring quality, improving consistency, and ensuring products meet both regulatory and customer expectations. We truly appreciate their partnership and their commitment to sharing knowledge with our community. Okay, and then lastly, I would like to introduce our speaker for today, Dr. Banu Sezer. Dr. Sezer is the Global Market Development Manager for Food and Feed at Anton Paar, where she leads strategic development for analytical, process, and quality control solutions across the global food and feed industry. She holds a bachelor's, master's, and PhD in food engineering from university in Turkey and has more than 10 years of industry experience spanning quality control, production, engineering, and research and development. Throughout her career, Dr. Sezer has worked closely with food manufacturers to improve food safety, quality assurance, and process optimization, helping businesses enhance both operational performance and product quality. We are delighted to have her with us today to share her expertise on the science of dairy quality, measuring what matters. Dr. Sezer, thank you for joining. The floor is yours.
For this wonderful introduction and also for allowing us to be present in the Food Collective initiative to reach the audiences today. I would like to thank you everyone who's joining us with these webinars. And today we will be exploring the food science behind the dairy quality. So when people hear about the word quality, I know they are often about passing the specification and meeting the regulatory requirement. But dairy is the quality is much more even just the regulatory or feeling the charts about certain numbers or leaving the aspect of only the requirements. So today I'll try to engage with more about the other aspects of quality that at Anton Paar we see through and through from start to end in our portfolio, and also support our customers, collaborators, and partners to get better decision making in every stage that they were wondering, working with, or having a project with. So it is about producing the product that are safe right now and consistent, stable, enjoyable for the customer. And I know it's economically efficient to manufacture it every day is a struggle. So every dairy product tells us a different story, from raw milk arriving at the factory to the product sitting on the supermarket shelf. And at every stage, this journey, measurements can help us to make a better decisions with a better and informed data available at our hand. So today's webinar, I'll try to engage with one of the very simple questions: which measurements matter the most and why? So we'll discuss the composition, texture, structure, and stability, and of course, how we can monitor this and measure these aspects one by one or in a more collective way. So let's begin with looking at what dairy quality actually means. When we think about the quality control, it's essential to focus on an individual test all the time. But I want you to think about a little bit outside of the box, and maybe its fat content, protein content, and microbiological results individually is not the answer of the quality on its own. But in reality, dairy quality is built strong throughout the entire production chain. So it starts at the farm level with the quality of the raw milk. I'm not sure how many of you were working with the farm level, but the parameters such as fat, protein, somatic cell count, microbiological load, and possible adulteration all determine the quality of the raw material before even reach to the process facility. So as the milk enters the production, our main focus shifts. So we need to ensure the effective pasteurization, maintain the microbiological safety, and carefully assess the quality of the material and the contamination and the composition all at the same time. We know that even small variations at this stage can affect the product consistency. So I want you to imagine yourselves at the entrance gate of the production facility. You are the quality responsible in charge, and you be expected to answer all these questions. Then this starts with the production. Then it comes to the processing quality and the shelf life, and of course, the regulatory compliance. So for product developers, for example, if any of you were working with new product development or R&D sector in dairy, the quality means something slightly different. So beyond the safety and composition, we are concerned with texture, mouthfeel, moisture, and sensory attributes, and of course, stability. So the question actually, will this yogurt be spoonable or drinkable? Will this cheese have expected structure become more important than the concerns of the entry level? And the story doesn't even end the product leaves the production line. Packaging, oxygen exposure, cold chain management, and storage conditions all influence how well the product reached to the consumer. So imagine you were working at the package development or packaging R&D. You will need to answer all the questions with the information gathered from the quality department or in the R&D for the new product. So when we talk about the dairy quality, as you can see, there are so many angles and so many points. We are really talking about a combination of composition, safety, texture, stability, process control, packaging performance, and of course, ultimately, the consumer acceptance. This is particularly relevant for a network like Food Collective because quality isn't created by one department. It involves farmers, processors, laboratory team, product developers, packaging specialists, and suppliers, of course. So it's an entire value chain from at the beginning of the raw material entrance and very final stage of the shelf. Throughout today's webinar, we'll try to focus on the measurements that help support at each stage of the journey. So please bear with me to see that how we can actually walk through from farm to the shelf. Actually, this slide really summarizes the philosophy behind today's webinar. In quality control, we don't measure something simply because we can. Every measurement should answer a question and support a decision. The first question always starts with what changed in the production. In dairy manufacturing, many things can change. Fat content may vary, total solids may change, water might be added unintentionally or through adulteration, of course. Proteins can denature during process. Fat droplets become smaller during homogenization. The yogurt structure changes during pumping. Oxygen may enter during filling or even packaging. So milk powder can become less flowable during storage or after spray drying. Once we identified what might have been changed, the next question, which analytical measurement can determine the change? Hopefully, before it happens. For composition, we may use density or refractive index. For texture-related questions, we may search with viscosity and rheology profiling. For stability, we may assess the particle size analysis, oxygen dissolution, oxidation stability, which may all provide an answer, but the right question at the right stage of the production process is the crucial to get the right answer. So a third question, generally the final question in the stage, is what decision does this measurement helps us to make? Because every data without a further decision process would be just a number, just a graph. So do we accept the raw milk with these data available? Do we adjust the fat content? Should we modify the formulation to make it more stable? Does the process require any correction because the particle size of the milk powder process is too small or too big? Or mainly, is the batch ready to be released? That's how I would like you to think about every analytical technique we'll discuss today. I know that you were joining us from a various stages of the research, R&D, production, so I will try to touch base at each stage with possible solution technologies so we can all take a look at the big picture together. So not just an instrument, but the tools that helps us to make a better decision making throughout the product chain that we will visit step by step. To make the just journey a bit more easier to follow, I've grouped the dairy quality into six main areas. We will begin with the composition because before we can optimize everything, we need to understand that actually happens in which compositional compartment of the material itself, subjected to change or may change. And next, we will visit the structure, which focuses on how these ingredients are physically arranged. For example, particle size, powder properties, or even microstructures. Then we will move on to the texture, where mainly viscosity, rheology, which help us to understand how the product will behave during processes and under certain stress in process like pumping, mixing, stirring, or even standing on the shelf if there is any phase separation is at risk. So the fourth area will be our stability focus, where we will look at the factors such as the solid oxygen, oxidation, or thermal behavior, all of which influence the shelf life. After that, we will briefly discuss about the food safety, focusing on sample preparation for trace elemental analysis. And we will finish all these six stages and all the topics to connect each other to make a one common goal, producing a product that are safe, consistent, and high quality. But we will see that how these measurement techniques and technologies will go hand to hand from start to finish. So let's start with the first journey of composition. Every dairy product begins with the composition. And before we think about the texture, shelf life, even packaging, we need to answer a very simple question. What is in the product and is it consistent? As shown on this process flow, composition has begun to control from the moment raw milk arrives at the processing plant. It continues through separation, standardization, homogenization, storage, and of course, final packaging and shipping. Each of these stages introduces the possibility of variation. Forget about being the incoming material's natural variation. That's why the analytical instrumentation and technologies are performed throughout the process, not at just the beginning of the stage. So, by continuous monitoring of the composition, of course, with the concentration, we can ensure the product consistency and reduce the variation between batches and try to optimize the production efficiency, which our ultimate goal is to deliver the same quality product at every time. So several analytical techniques contribute to this process. And we'll begin with one of the most fundamental ones, which is density. The first parameter I'd like to discuss is the density, one of the most fundamental measurement in dairy quality, of course. Density is a basic physical property, but it tells us a surprising amount of dairy product information because it is directly related to the composition and it provides a very valuable information about the product itself, about the purity, about the concentration. And in the dairy industry, we know that density is used throughout the production not only for routine quality control, but also for mass to volume conversions and fat determination, and the calculation of course, total solids. Many of you may remember the traditional methods such as hydrometers or lactometers. Today, these have largely been replaced by digital density meters because they offer a much higher accuracy, better repeatability, and much faster measurement times. Another important advantage is the excellent correlation between density and composition. So as you can see the graph, the density-based measurements correlate very well with the laboratory references values for fat, total solid content, solid non-fat content. So rather thinking of density as just another physical property, it is better to think of that it's a rapid indicator of composition, helping us to verify the product consistency throughout the process. Because I know the first question will become to how this measurement will be translated into daily life. So in this graph with the table, you will be able to see the real application. The table on the left compares the density of several dairy products that you will notice skim milk has the highest density, while cream has the lowest one. The reason is quite simple. Fat is less dense than the water, so as the fat content increases, the overall density decreases. At the same time, solids such as proteins and lactose also influence the final density. Because of this relationship, density becomes much more than just a measurement, but it practically quality control tool for the material itself. For example, it helps answer the questions, is the raw milk within specification? At the very fast, very at the end of the facility. Has the milk been diluted or adulterated at any way? Has the standardization process achieved the correct fat amount? All can be measured by a single technology that used a very simple physical parameter. You may also ask the questions that are the filling volumes accurate before the batch release? The graph on the right side reinforces these questions with a good answer because you are able to see the strong agreement between density measurement and the laboratory references in this graph. What this means in practical that simply density measurement can provide an immediate confidence that the product is meeting the specification and allows manufacturer to make faster and more informed decisions. But is it alone? No. Another important parameter that we generally see in dairy composition is total solids. Milk is a complex mixture and consisted of primarily water, fat, proteins, lactose, and minerals. In processed products, such as sweetened condensed milk, additional ingredients like sucrose also contribute to the overall composition. Together, these components make up the total solids and sometimes referred as the dry matter. The total solid content naturally varies depending on the factors such as animal, feed, season, processing conditions, of course. And that's why the monitoring these parameters is essential for maintaining the consistent quality. Traditionally, total solids are determined by gravimetrically, basically evaporating the water and weighing the remaining solids. While this method is highly accurate, it can take several hours to complete the method and get the results, and it also user dependent. Unfortunately, total solids have a very strong correlation with refractive index. The illustrated graph shows that we can determine the total solids in a few seconds without any user interference, any evaporation needed, just as the sample is using its own state by simply measuring the refractive index. For routine control, this offers a significant advantage. Instead of waiting for the laboratory result, we can receive immediate feedback and react much more quickly without any human interference in the measurement. So far, we've seen the composition. But what's the product itself is the main question. I assume that you're also working with the product development and research of the product composition itself. The most important question of the product itself that how are those components arranged inside of the material? That's what we may define as a structure. In dairy product, structure includes characteristics such as fat droplet size, particle size distribution, agglomeration. In dairy powders, powder behavior, powder density, powder flow. All these are physical properties. They have a direct impact on the product performance. They influence how a product dissolves, for example, an instant drink, how it flows through pipes, and how exactly will behave. Let's take a look at the particle size at first. Particle size is one of the key structural parameters in dairy products because it influences many different characteristics. It affects appearance, mouthfeel, stability, processability, and even rheological behavior. That's why particle size analysis has become such an important tool, both quality control and product development departments. Depending on the sample and information we were looking for, different analytical techniques are available. In these different techniques, a very small particles such as proteins and fat emulsions, we use dynamic light scattering. For larger particles and powders, including milk powder, infant formulas, any chocolate, milk mixes, coffee creamers, or any type of emulsions, we offer laser diffraction technologies to provide a broader range of measurements. And when particle shapes is also important as much as the size distribution itself, we advise using dynamic image analysis to be able to get the morphological behavior of the sample. So rather than asking which technique is better, the real question that we always want to ask, which technique is appropriate to get the correct answer that we were looking for. I will briefly mention about each technique so you may apply to your own projects or ask your own questions to get which technology will be the best suited to answer the correct questions and the questions that you're dealing with. Let me start explaining by dynamic light scattering. We shortly call it as DLS. This technique is designed for measuring very small particles in a suspended liquid. When particles such as milk proteins or fat droplets are dispersed in a liquid media, they move continuously due to Brownian motion. A laser passes through the sample, and as these particles move, they scatter the light in different directions. The detector records these tiny fluctuations in the scattered light, which gives an intensity over time. Using the functions on these instruments, generally we calculate the hydrodynamic particle sizes. And the mathematics behind this calculation is quite sophisticated, but from a practical point of view, the important information is the particle size itself. In many dairy applications, DLS helps us to characterize the proteins, emulsions, and very fine particles. It also allows us to monitor changes in particle size during processing and evaluate the stability of the liquid dairy product. So by measuring the particle size that are far too small to see, DLS gives us valuable insight into product's microstructure and mainly the stability. On the other hand, if the particle size gets a little bit bigger, so when we move from nanoparticles to larger particles or powders in general, we use different technique. It's called laser diffraction. This is probably one of the most widely used particle size analysis technique in food industry. The principle is relatively simple. When a laser beam strikes a particle, the light is diffracted or scattered and around it. The diffraction angle depends on directly the size. So basically, smaller particles scatter light over a larger angle, while larger particles scatter the light over a smaller angle. By measuring this diffraction pattern across a wide range of angles, the instruments calculate the complete particle size distribution of the samples. This makes laser diffraction an excellent instrument, such as milk powder analysis, infant formula, chocolate powders, chocolates itself, milk itself, coffee creamers, or any type of emulsions. The only restriction is the size that you were looking for. And how do we do that? Is a very, very simple. The detector records the intensity and creates a unique pattern. Mainly, the software compares this pattern into mathematical modeling. By identifying the best fit of the mathematical modeling, it calculates the particle size distribution. This is much more informative than a single average particle size that you were doing with any type of sieving method, because you don't get one particle size value, you get the size distribution. Because samples mainly contain different size of particles altogether. They have fine particles, coarser particles, and a broad size distributions. For dairy products, this information is extremely valuable because it helps us to evaluate homogenization efficiency or monitor dairy powders quality or improve formulation if dairy dissolutions like baby formulas or ensure consistent product performances. And third technique generally used this in industry is dynamic image analysis. Unlike laser techniques, which calculate the particle size from a scattered light, image analysis captures images of individual particles. The workflow is actually very straightforward. At first, the sample is dispersed so that the individual particles can pass through the measurement zone, and then a high-speed camera captures thousands of particle images, and dedicated software analyzes the particles individually. This provides not only the size distribution, but it gives more detailed information about the shape, mainly the morphology of the particles. The major advantage is if you have two powders that have exactly same particle size distribution, but one of them contains spherical particles, the other one contains a bit more irregular one because of the size reduction process, mainly called milling process. They will behave a very different during mixing, conveying, pressured packaging, or even instant dissolutions of any instant drinks. For example, imagine a food milk powder and infant formula powder. This additional shape information provides a much more complete understanding of these two different powders, because you may imagine that any food milk powder or any infant formula powder do not give a specific same dissolution characteristics. If you want to add water and mix it, they don't dissolve at the same time. One of them is faster, the other one is slower. So depending on your intent, which one will affect, even though their size distribution is the same, will be influenced by the shape of the powders itself. So let me give you some practical examples using an infant formula. Particle size plays a crucial role in infant nutrition because it's directly influences the mixing, solubility, stability, and ultimately the nutrition delivery. But it's also a toddler formulas or even milk powders, protein shakes. Those are all sharing the same common challenges when it's come to the particle size. Infant formula is a complex product containing proteins, carbohydrates, plant based oils, vitamins, minerals. many others look like protein powders or milk powders or any ready-to-eat shake powders. Because of this, we naturally see a very broad particle size distribution of this type of product, generally extending the product range. 1 micrometer goes up to 1000 micrometer. The main particle population, as you can see from the graph, appears between 100 and 200 micrometers, with smaller shoulders representing the finer ingredients of the formulation. We generally compared in this study the original infant formula with different formulations containing 1 to 5% sugar addition. Although this seems to be a very small formulation adjustment, the particle size, as you can see, changed quite noticeably. The proportion of a larger particles increased while the finer particle fraction is decreased. This illustrated us the giving a very important point. Even minor formulation changes, we can modify the physical structure of the product, which will definitely change the further aim if you want to dissolve with a water, if you want to mix with another powder, if you want to pack under pressure to make sure that it's tightly packed, or convey from silo to hopper, or in the conveyor belts, or in any type of pressured pipelines. Another excellent example on this topic is to evaluate the homogenization efficiency, because when we talk about the particle size distribution, everyone has a tendency to imagine a powder, but particles are also included in liquid medias, and milk, especially dairy products, are one of the excellent example of this. If you look at a glass of milk, you only see a very fine white colored liquid, right? But it's exactly an emulsion having a different particle sized fat droplets. And that's why in every dairy process, a step called homogenization plays a very critical role in the production. And the homogenization oftenly assessed by the efficiency. So by reducing the size of the fat droplets in the homogenization, it creates a more stable emulsions. It proves and improves the consistency and helps to prevent the cream separation during storage. So on the graph on the left, you can see that the how particle size distribution change as the homogenization, or in case of the sonication, increases. The particles gradually become smaller and the distribution shifts towards the final particles. In the middle graph, you can see that the increase in homogenization efficiency, that the process becomes aggressively more effective. And in the final graph, you can see that the strong relationship between homogenization efficiency and the particle size parameters. This is important because it shows that the particle size analysis is not simply describing the product. It also provides a fast and reliable way to whether your homogenization process is performed as expected, which later on will reflect on creaming, phase separation, or any kind of flocculation or flotation. Basically, these fat particles come together, go up high, or any other particles inside of the liquid media clogs, creates big agglomerates, and goes at the bottom of the product itself on the shelf. When we move from liquid to powder medias and talk about the particle size, as I said, everyone thinks about the powder. Well, powder is a very critical topic, especially in dairy product, because instead of asking how these particles behave, how large of these particles, how small is this, we need a bit more practical understanding, because even if the particles are large or small, we need to make an informed decision. We talked about a very early of this webinar that we will decide using this data to make an action. So how do these particles pack together is a more appropriate question, and what will be result of a making decision regarding packing it or not packing it. So that's where bulk density and tap density measurements become a very valuable tool. Imagine you have fine powders and granular materials behave differently depending on their cohesiveness. Basically, the particles want them to be together or separated from each other, and their packing characteristics. So these properties mainly influence formulation or storage or transportation and efficiently the packaging. So in these type of situations, we generally look up to the measurements called tap density to understand the mechanically how this powder will behave. Tap density is a measurement that mechanically tapping a container filled with a known quantity of powder until the volume no longer changes. So basically on the image you can see that the volumetric flasks on top, we fill the powder and then we have a vertical movement on the powder to understand that volume will change and how long will it take, and once the volume change stops, what will be the tapping volume. Compared to the bulk density, the tap density gives us a very valuable information about these particles' cohesiveness and flowability, of course. As a good example is the slack fill, often seen in protein powder containers. The containers sometimes wonder um, how this will be filled. But you may imagine that you grabbed a powder container or a milk powder container or protein powder container. You open it up and you see that there's a certain empty area. This is called a slack fill. So in reality, the empty space is usually intentional. It allows to powder to settle during transportation without becoming excessively compacted or overflowed. Basically, nobody wants to open up a package and get their milk powder a big chunk or big agglomerates. Everybody wants to have like a scoop of it and easily distribute the powder. By understanding the bulk and tap density, we can optimize packaging volumes and improve the transportation efficiency and reduce the unnecessary packaging while still protected the product quality and of course the consumer perception about it. But bulk density tells us how powders pack together. True density, on the other hand, tells us about the particles themselves. This measurement generally is performed using a gas picnometer, where an inert gas is filled, such as helium or nitrogen, fills the space around the particles and within any open pores. And we use a Boyle's law, the instrument accurately determines the true volume of these particles. Why it's important? It provides a valuable information about a material composition and morphology and consistency. So we will try to answer using this type of technologies how powders behave during processing. That's where we try to understand how much it will get benefit from the bulk density. But please keep in mind that this is not specific for any powder. It's easier to explain the process using a powder examples, but you may want it to measure a cold dairy product such as ice cream or whipped cream. Whipped cream packaging is a pressured packaging. You need to know the precise amount of material goes into those pressure cans to be able to accurately flesh out the sample on the nozzle tip. Or any type of packaging who's similar to toothpaste. You can fill it with a dairy paste or cream cheese or different type of packaging which require specific fill volumes depending on not the bulk but its true density. So far we talked about the how the powders and density effects, but there is a very important parameter that we need to understand to give a complete picture of these materials. It's called rheology. Mainly in rheology, we select two different topics to explain it, both in viscous and viscoelastic materials and powder materials. Since we touched the powder materials in here, I'd like to briefly talk about that how the powder handling, especially in protein powder manufacturing or formulation, milk powder manufacturing or formulation, we can benefit from powder rheology. Because mainly, if you're dealing with any type of powder operations or researching dairy powders, flowability, compressibility, permeability, bulk density, or wall friction, these are the fundamental topics that you were working on. These characteristics can all be determined how powders behave, either mixing, conveying, storage, packing, or being another powder at the same time. So each of these parameters will answer, of course, different questions, but can be obtained from a single technology. So this technology generally calls as powder rheology. The graph on the left side compare two different coffee creamers. It's easier to explain on an example. Visually, these powders look almost identical. However, when we measure their cohesion strength, clear differences were observed. So the coffee creamer A has a lower cohesion, and coffee creamer B, on the other hand, is more cohesive. What does this mean? This means that coffee creamer B, while this may not be obviously visual, it can lead to challenges during in transport, storage, packaging, and also for dissolution. And please imagine when we use coffee creamer, which operation needs to be added coffee creamer? We need to get them to be dissolved equally. So let's take a look at the right side graph. We see another important powder property here. Here, skim milk powders show significantly higher interaction with the equipment surfaces than infant formula. We say increased wall friction can contribute this kind of problem. And in real life, if the wall friction increases, what happens? The result is either bridging, funnel flow, fouling, or rat hauling, all of which reduce the production efficiency and disrupt the process. So these examples demonstrate that if we use a powder rheology to understand how two powder mix each other, how well it will mix each other, how it will their cohesiveness being compact together, or how exactly they will flow, we can answer these questions before even the problem arises, or we can optimize the sample that we'd like to add to our formulation, or vice versa, exclude from our formulation. But rheology is not just about the powder itself. In dairy, if we go to a grocery shopping today, the aisle with 80% liquid and viscous materials. Up until this point, we focused on what the product contains and on how physically structured. But the next quality attribute is probably the one of the consumers first notice and make a decision on it, which is how the product feels itself, how the consumer feel about it. Is the yogurt creamy or watery? Does the butter spread easily? Is the ice cream smooth or spoonable? So those characteristics all related to texture, and understanding the texture means mainly understanding the viscosity and rheology. So in this section, I will explain a little bit about the viscosity and rheology and how the logic behind it works. So I can hear it. What is exactly the rheology as the first question? Quite simple. Rheology is the science of how materials flows and deforms. So one important thing to remember is that the dairy products do not behave the same way under all same condition. So think about a cup of yogurt. When it's sitting on the supermarket shelf, it's almost solid. When you stir it, it starts flowing. And when you pump it, it behaves differently again. Once you eat it, it experiences completely different forces because of your teeth, because of your tongue, because of your jaw. So exactly the same product applied different type and shape of forces will result in different response. So that's why shear rate, something a rheological parameter, becomes an important concept. We say the low shear rate represent the conditions such as storage and product, thinning the containers or shelf. Higher shear rates generally represent pumping, mixing, filling, or even sometimes swallowing. As shown on the right side of the slide, rheology supports every stage of the product life cycle. So during formulation, it helps optimize the ingredient. During production, it ensures smooth processing. And during storage, it predicts the stability. And finally, it helps to understand the consumer experience. So instead of asking, what's the viscosity of the material? What's the viscosity under the condition that matter is the accurate question. So let me give you an example. Let's take a cup of yogurt. Yogurt is the perfect example in this scenario. Its viscosity influences almost everything from processing to consumer acceptance. And it determines whether the product is drinkable or spoonable, whether it feels creamy, and how well it behaves during pumping and filling. On the slide, you can see three different types of viscosity measurement, and each one answers a different question. The single point test generally used for routine quality control analysis where the goal is to compare one batch to the next one in the standardized condition. The yield point test tells us that how much force is required before this yogurt starts to flow. This is particularly important for products that should maintain their shape in the cup, still be easy to spoon or pour. And the third one is the time-dependent test shows us how the viscosity changes while the product is continuously stirred or pumped. Yogurt is a classic shear thinning material. As shear increases, which means that as we start mixing and mixing and mixing, its viscosity decreases. That's actually beneficial because it allows the product to be pumped and filled more easily without requiring excessive energy. To obtain reliable results, we use vane spindles, which minimize structural disruption and prevent the wall slip, making them particularly suitable for delicate dairy products such as yogurt or creams. So rather than performing a single viscosity measurement, we are evaluating different aspects based on the right questions and asking the related one of the instrument. Of course, texture doesn't happen by an accident. It's created through formulation. And dairy generally is not a single formulated one item product. One of the most common ways to modify the texture is using hydrocolloids or thickening agents. Many of the dairy drinks include both at the same time or one of them. So examples generally like xanthan gums, guar gums, carrageenans, pectins, gum arabics. You may also imagine that dairy desserts like jams and jellies that contain high amount of dairy or ice cream desserts. These ingredients increases the viscosity without significantly changing the flavor mainly, and particularly interesting gum types will change their viscosity and texture quite high. So even at very low concentrations, it produces highly viscous solutions and generally shows a very good shear thinning behavior. That means the product remains thick while standing still, but flows much more easily during pumping, mixing, or pouring. This improves both processing efficiency and also for the consumer acceptance. So mainly, challenge comes with the thermal stability. When you take a look at the viscosity values, you always see that there is a temperature associated nearby the value because temperature is the fundamental characteristics of viscosity measurements. It's a temperature dependent technique. So while you were doing the method and the measurement settings, please keep in mind that you need to control the temperature of the sample. That's why we always often say that the consistometers unfortunately do not have a controlled temperature. So please make sure that sample temperature is the same while you're repeating the measurement. As shown in the graph on the slide, xanthan gum maintains relatively stable viscosity over a broad temperature range, helping dairy products maintain the consistent texture from refrigerated storage to the processing and normal storage. The comparison at the bottom of the slide also demonstrates that how different milk-based beverages develop different viscosity profiles depending on their formulation and depending on the temperature they took the measurement. So if you will do a viscosity measurement, I will highly advise the keeping the sample temperature constantly on the same set during, before, and after the measurement to make sure that you repeat the correct method at the correct values. Simple viscosity measurements tells us how a product flows. However, advanced rheology tells us why it behaves that way. And mainly, new product development and R&D, especially the formulation, requires an advanced rheology profiling rather than just a single point or multi-point viscosity measurement. Let's look at the three different dairy products in here. The first example is the milk drinks. Adding a thickening agent creates a weak gel, generally, and improves the mouthfeel while maintaining the drinkability of the product. But which thickening agent that you were looking for needs to be addressed with a rheometer, because rheological measurements help optimize the balance between texture and how it will swallow, basically the behavior during movement. The second example for it is butter. We'll all experience butter that's difficult to spread straight out of the refrigerator, right? By measuring its rheological properties at different temperature, we can optimize the formulation and remain firm enough for storage, but still spreadable easily. And an ice cream example. You see that the rheology predicts characteristics that consumers notice: scooping, melting, being creamy, being icy. These are all related to the product's rheological behavior. Although these products are very different, the principle remains the same. Rheology transform subjective sensory impressions into objective and measurable parameters that can be optimized during product development or altered. Let's look at the closer look at the butter example. One of the most important quality attributes in butter is spreadability, right? And this changes dramatically with temperature. Using a rheometer, we can monitor how the internal structure responds to this deformation. At around 10 Celsius degree, butter behaves as much stiffer on the side. Its elastic components generally dominates, so instead of spreading smoothly, it tends to fracture or break. So knowing this will help us that what type of butter we will produce and how it will behave will be an answer. Our rheology and measuring a rheology ultimately give us a translation into a mathematics, to a feeling, to a process, and it's also a decision that this formulation is creamier when compared to the other one and smoother and pleasant. And of course, it will behave in the mixing with the mix force. It will behave in a way in the pumping. So all the flow and material characteristics will be determined using a rheology measurement. We've spent quite a bit of time discussing how to produce the right dairy product, but producing is the one part of the challenge. Mainly, keeping it through the shelf is also an extremely challenging topic. That's why I want to also slightly discuss about which factors will affect on the stability of the product itself. Several factors influences the stability, but there are particularly important topics called dissolved oxygen, which generally accelerate the oxidation, and of course oxidation stability, which affects the flour and shelf life. and the thermal behavior, which generally determines how product respond to the temperature during processing and storage. If we understand these parameters, we can protect the product, keep the quality intact after the process itself. One of the most overlooked quality parameter in dairy product is dissolved oxygen. We can see it, but oxygen has a significant impact on the product. High oxygen levels accelerate oxidation, mainly reduce the vitamin stability, affect the flavor if it's a flavored dairy drink, and ultimately shortens the shelf life. So we keep dissolved oxygen as low as possible in a product, particularly for packaged dairy product. We extend the shelf life, we improve the consumer acceptance, and we also contain the quality of the material itself for a longer period of time. Oxygen measurements are valuable throughout the production. They generally help verify the packaging performance, and it allows us to monitor deaeration efficiency and can even provide information about microbiological activity to a certain extent. So we will either use it something in line to measure it, or through the PET bottle or glass bottle or the carton itself. The dissolved oxygen needs to be controlled and under observation for the process and the packaging life cycle to make sure that quality is sustained. Let me give you an example. This slide demonstrates that why oxygen measurement is so valuable in everyday production. On the left side, you see dissolved oxygen measurements from different dairy products packed in a glass bottle, PET bottle, and cartons. Even though the product may appear similar, their oxygen content varies considerably depending on both the packaging material and the filling process, of course. This means that dissolved oxygen becomes an excellent process indicator. If oxygen level suddenly goes up, it may suggest changes in packaging performance, deaeration efficiency, or product handling. And the diagram on the right illustrates the same concept within the duration of the process. During aeration, oxygen is removed from the packaging and helping improve the product's stability and extended shelf life. Inline monitoring helps the 724 observation of this process before the packaging happens. So the oxygen measurement help us to monitor both process itself and the quality of the final packaged product. So far, we looked at the measurement that helps us to understand the composition, the structure, texture, and of course, the stability. The final quality dimension is food safety. And when we talk about the safety, there are many aspects of it in terms of safety, materials that will be under harm, including adulterants, any kind of foreign materials, microbiological safety. But I want to briefly mention about the elemental safety, which is one of the most important safety features as well. In elemental analysis, dairy is a complex matrix, and they contain fat, protein, carbohydrate, minerals, and many other components as well. That makes elemental analysis quite a bit challenging. Before the trace element can be measured accurately by any technique called either ICP-OES, ICP-MS, or atomic absorption, the most critical part is sample preparation that everyone actually overlook. This step is generally underestimated because incomplete digestion can result poor recoveries, contamination, inaccurate analytical results. However, we are more focused on this aspect to measure the analysis itself and preparing it. So we often focus on the instrument, but the quality of the final result actually depends on how well did you prepared and more specifically digested the sample free from the media. That's why microwave digestion has become much more important part of this analytical workflow. I want to show you a practical example. In this study, several different dairy products, including raw milk, butter, yogurt, cottage cheese, curd, or skim milk powders, were digested together with a single run. Normally, these products behave very different during digestion because of their different fat and protein contents. But depending on the selecting the newest technologies called HVT vessels with smart vent technology, all samples were successfully digested prior any batching or pre-processing. As you can see on the left side, the digestion solutions are completely clear and colorless, indicating a complete digestion. That's why we offer and generally advise using a microwave digestion systems when compared to old and traditional hot blocks. More importantly, the elemental recoveries shown in the graph agree that the certified reference material results. This tells us that both excellent digestion and the analytical accuracy were obtained because sample preparation is the core and the fundamental principle of this elemental safety analysis using any type of elemental analysis method. Before we move into the Q&A session, I would like to leave you with one additional resource. Today, we covered a wide range of analytical techniques and practical applications. Because of our limit time together, I could kindly only share selected some examples and be able to highlight some key principles behind the measurement technologies. Many of these applications and studies we discussed today include much more detailed experimental data, complete measurement procedures, and additional graphs and real applications as well. So we compiled all of this into our field guide testing solutions ebook free of charge. If you would like to explore these topics in more details, please simply scan the QR code on the screen and download your free copy. And I hope it will be useful for your reference, your laboratories, your research environment, and for your studies and projects. And before I hand over to Jana, I would like to invite you our two upcoming seminars in Johannesburg and Cape Town about food quality, safety, and innovations. This is a free of charge seminar. Please feel free to sign up. We will be delighted to have you. That's bring us the end of today's webinar session, and we can move on to the Q&A section.